Okay, so for day 4 of Fluids Online, we are going to be talking about buoyancy. Oh yeah. Nothing else for it here. Let's just go to the definition here. The definition is defined using Archimedes' principle. Maybe you've heard of it. Hopefully, maybe once you'll hear it, you'll shout Eureka. But anyways, what this says is the force of buoyancy. Force of buoyancy, or buoyant force, whatever, is equal to the weight of fluid displaced. Nice. Now, there's one key thing here. I wasn't just being quick. It does mean weight. So weight is a force. So here's the deal. If we wanted to calculate this, the force of buoyancy, we'll call it FB, is going to equal mg, where m is the mass of fluid. However, we don't usually measure fluids with mass. So this is going to be a little review here. We know that density is going to be mass divided by volume. So that means that mass is going to equal density times volume. So what we're going to do is we're going to take this guy and substitute it in for mass. So the formula is really going to look like the force of buoyancy is going to equal rho v g. All right, so this is density, and this is important, of the fluid, okay? And this is volume displaced. Usually it'll be the volume of the block or whatever that gets dunked in the water. And this is just gravity. Okay, so this little substitution here for density and volume, we're going to do that a lot today. Okay, so you had your warning here. So Archimedes' principle. One thing to notice for direction, right, because this is a force, that means it's a vector, is this is always opposite of gravity. The reason why is because the water, the liquid, is always going to be pressing down. So that means that the object is always going to be lifted up because it's the water trying to fill in the gaps and it's going to push whatever brick it is up. Now, it's not going to float necessarily, but it'll go up a little bit. Okay, so let's do a practice. So we have a brick of iron. Iron is that density is thrown into the water. If it's this by that, what is the weight in the pool? So it's going to weigh less than it would normally, right? I think we all are aware of that. Let's draw a picture of what will happen here. So here's the pool. Here's our brick of iron. Oh, hold on. Iron has to be red. So there is the iron. Okay. So now there's two forces that are acting on this. One is the weight of the gravity, right? Fg, your old friend. And the other is going to be your buoyancy force, Fb. They're going to be going in opposite directions, so they're going to subtract from each other. Now, the difference between the two of them is going to be your normal force normal, and that's really what they mean by weight. So if you were set it on a scale, the force from the scale would be the normal force, all right? So let's set this up here. Now, if we wanted to set him up, what we're going to have is force normal is going to equal your force of gravity minus your force of buoyancy, right? Because these two together make force gravity, so you subtract it to get the other one by himself. Okay. Now, force normal, that's what we're solving for, so let's just leave him off on the side forever. Force of gravity, that's easy, mg. And we're going to subtract rho vg. Okay? Now, this is for buoyancy. Now, something else in mind, just like before, we could figure out the mass of the block of iron, but we really won't need to. What we're going to do is we're going to plug in the density of iron times the volume of iron times gravity minus rho Vg. Now, these are not the same. The one on the left is talking about for iron, and the one on the right is talking about the water. But they're going to have the same volume. So let's think about it here. This is for iron, so we're going to have 7874, right? For volume, the volume of this guy is going to be 0.15 times 0.20 times 0.40 times gravity. Okay, and then we're going to compare that to the force of buoyancy here. The density is only 1,000 because it's just the water that's displaced by that brick times the volume here. The volume is going to be the same thing, so 0.15 times 0.20 times 0.40 times 9.8. Ooh, just made it. Okay, so we combine all those together and then subtract it. So that means the weight of it is going to be 808 newtons. And that makes sense. It should be less than the normally would. So if you multiply that out, the normal Fg is going to be, about 950 newtons if you wanted to figure that out. And that should be less. So the force of buoyancy is, in this case, about 140. All right, looks good. Now, we're going to talk this time about when things float. All right, when they're floating, okay? Now, the key distinction here for floating means that the force of gravity is going to equal the force of buoyancy, okay? Sound good so far? Now, the important thing to realize for this is that not all volume will be underwater. This is the most important thing, because if you had, an iceberg, right? An iceberg floats something like this. Okay, you have mg is equal to rho Vg. Now, if we did the same thing we did last time, so we have rho Vg is equal to rho Vg. These guys here are not equal. The volumes are not equal anymore. This volume here is the volume of water displaced. So that is this guy. So it's this part of the iceberg here. Whereas this volume right here, this is the volume of ice, which is going to be this box here. All right, the whole thing. So that's where the differences come in for floating. All right, we're going to do an example here real quick. Let's do it. We have a block of wood is floating in the water. It has an area of 60 by 80, right? That's like, parallel to the surface of the water. There's 20 centimeters below the water and 50 centimeters above. So here's my block of wood. Gorgeous. Let's put some measurements on there. We'll call this guy the 60. We'll call this one the 80. There's 20 below and 50 above. So that means our surface of water is going to be something like this. All right, we're trying to figure out what's the density of the water. Well, we know a little bit about the forces here. There's going to be a force of gravity, and there's going to be a force of buoyancy, and those two are going to be equal to each other because it is floating. If they weren't equal, it'd be moving up or down. So let's set them up equal to each other. FB is equal to FG. FB is going to be rho Vg, and that's going to equal, I'm just going to go for it, rho Vg. Right, but the volumes are different this time. So density for buoyancy, it is buoyancy, so it's going to be the density of the water times V. To figure out the volume, I'm going to have 0.6 times 0.8 times 0.2. Just the 2, because that's only the part that's underwater here. So it's just this box here times gravity. And that's going to equal rho. We don't know what the weight of the wood is, or the density of the wood is here, but we do know its volume, so we're going to have 0.6 times 0.8 times 0.7, right? It's going to be 0.7 because it's the whole thing, right? So the whole block of wood is going to have this volume, right? Times gravity, 9.8. Looks good. So we're going to solve this now. And I know that you can see it, and yes, you should. Cross out the 9.8s. 9.8s cancel out. You can also cancel out the 6 and the 8 because they're the same on each side too. So it doesn't matter this cross-section area. It will work the same just with the depths. Now, when we multiply this guy all around, so we're going to have the density is going to equal 286 kilograms per meter cubed. And that's the density. You can see how specific gravity ties into this as well here. Okay, one more problem. This will be the fun one. A balloon has a volume of 0.3 meters cubed. What's the force of tension on the string? And there's the density of air, density of helium. Ooh, do you think you can figure it out? I wanted to put a fun one so I didn't disappoint you. Draw a picture of it, see if you can figure it out. Pause the video and come back to you afterwards. Go! Okay, so here's my balloon. So the balloon has two forces on it. The first one is the force of buoyancy. The second one is the force of gravity. It's got a volume of 0.03 meters cubed. All right, let's figure it out. Oh, there's one more force, my bad. One more force is tension. The force of tension is pulling it down, right? So this means that the force of tension plus the force of gravity is going to equal the force of buoyancy. That should make sense. The heavier it is, the less tension it'll need because it's getting pulled down. So we need to solve for force of tension. So force of tension is going to equal force of buoyancy minus the force of gravity. Now let's plug in the values here. So buoyancy is going to be rho Vg. And then gravity is also going to be rho Vg because this is m in disguise here. Now, density for buoyancy is going to be density of the air. So it's going to be 1.2 times volume, which is 0.03, times gravity, which is 9.8. And that's going to be minus density of, for mass, is going to be density of the helium. So it's going to be 0.2 times 0.03 times 9.8. Math, 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 and we are going to get a force of 0.29 newtons. And that's it. It's not going to be very much. It's a small balloon. And, you know, these are very similar densities, sort of. It's only times 6. All right. Hey, so that's how that works. Okay, there's plenty of fun to be had with this kind of stuff. Enjoy the practice, like and subscribe.